Case 2, two equal real roots. Welcome back, everyone. In our previous lesson, we introduced a very powerful tool called the discriminant, which we denote as d, where d equals b squared minus 4ac. As we discussed then, this value is incredibly useful because it allows us to determine the nature of the roots of a quadratic equation, specifically x squared plus bx plus c equals 0, without us having to go through the long process of solving the entire equation. Today, we are going to narrow our focus. While we previously looked at what happens when the discriminant is positive or negative, this specific subsection focuses on the unique scenario where the discriminant is exactly equal to 0. Understanding the concept. Now that we've introduced the discriminant in the previous slide, let's dive deeper into what actually happens when that value equals 0. You'll notice that when the discriminant is 0, the quadratic equation stops producing two distinct, different values for x. Instead, the two solutions merge into one single value that is repeated. To really understand why this happens, let's walk through the mathematical breakdown together. First, we start with our specific condition. We set the discriminant, which is b squared minus 4ac, equal to 0. Next, let's look at how this affects our quadratic formula. As you remember, the general quadratic formula is x equals negative b plus or minus the square root of the quantity b squared minus 4ac, all over 2a now, if we substitute 0 in place of that entire discriminant part, the b squared minus 4ac, the formula transforms. It becomes x equals negative b plus or minus the square root of 0 all over 2a. Finally, we simplify. Since the square root of 0 is simply 0, that plus or minus part of the formula no longer creates two different mathematical paths. Adding 0 or subtracting 0 doesn't change the numerator, so the equation simplifies beautifully to just x equals negative b over 2a. Because both the plus and the minus operations lead us to the exact same result, we conclude that the quadratic equation has two equal real roots. You might also hear mathematicians refer to this as a repeated root or even a double root. Keep this logic in mind, because in the next slide, we're going to see how this exact principle applies to a real-world physics problem. Real-world application example. In the field of physics, the discriminant is a powerful tool used to determine if a specific state or threshold is just barely achieved. To make this concrete, let's consider a scenario involving motion. Imagine a ball is thrown vertically upwards, and our goal is to find the exact time, which we will call t, at which the ball reaches a specific height. For this example, the height of the ball at any given time t is modeled by the quadratic equation. H equals negative 5t squared plus 20t minus 20. We want to find the time t when the height, h, is exactly 0 relative to a specific platform. Let's walk through the solution step by step. First, we need to identify our coefficients. We set our equation equal to 0, so we have negative 5t squared plus 20t minus 20 equals 0. From this, we can clearly see that it equals negative 5, b equals 20, and c equals negative 20. Next, we calculate the discriminant, which we denote as d using the formula we learned in the previous slide. D equals b squared minus for a c plugging in our values. We get 20 squared minus 4 times negative 5 times negative 20. When we calculate this, 20 squared gives us 400, and 4 times negative 5 times negative 20 also results in 400. So we have 400 minus 400, which leaves us with a discriminant of 0. Now, let's determine the nature of the roots based on this result. Since our discriminant is exactly 0, we know from our earlier discussion that the equation has two equal real roots. In the context of our physics problem, this tells us something very important. The ball reaches that specific height at exactly one single moment in time. It essentially just touches that height level before immediately beginning its descent back down. Finally, let's find the actual value of that time. Since we are dealing with the case where the discriminant is 0, we don't need the full quadratic formula. We can use the simplified version we derived. T equals negative b divided by 2a. Substituting our values, we get negative 20 divided by the quantity 2 times negative 5. This simplifies to negative 20 divided by negative 10, which gives us a final answer of 2 seconds. So at exactly 2 seconds, the ball reaches the target height. Now that we understand the mathematical theory behind why the discriminant being 0 leads to a single repeated root, let's see how this actually applies to a real-world situation. As we move to the next slide, I want you to pay close attention to some common pitfalls students encounter when performing these types of calculations. Common mistakes to avoid. First, please be careful not to confuse the discriminant being 0 with the root itself being 0. I often see students think that if d equals 0, then x must also be 0. This is a mistake. Remember, a discriminant of 0 simply tells us that the two roots are identical. It doesn't tell us what that value actually is. To find the actual value of the root, you must still use the simplified formula, which is negative b over 2a. Second, watch out for sign errors when dealing with the variable b. When you are calculating negative b over 2a, students frequently forget to flip the sign of b. It is crucial to remember that if b is already a negative number, then negative b becomes a positive value. Finally, pay close attention when calculating b squared. A very common mistake is forgetting that any real number, whether positive or negative, results in a positive number when it is squared. For instance, if b equals negative 4, then b squared is negative 4 squared, which equals 16, not negative 16. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of the discriminant, it is very easy to make small computational errors that can lead to the wrong answer. Keep these points in mind as we move on to our final summary of the key takeaways. Key takeaways. First, let's revisit the essential condition we've been discussing throughout this session. Two equal real roots occur if, and only if, the discriminant, which is b squared minus 4ac, is exactly equal to 0. This is the magic number that tells us our two potential solutions have merged into one. Second, regarding the root value itself. Remember that when this condition is met, the two roots essentially collapse into a single, repeated value. Instead of dealing with the full quadratic formula, we can use the simplified version, where x equals negative b divided by 2a. This is the specific value where our equation holds true. Finally, I want you to visualize this graphically, as this is often the most helpful way to understand the concept. If you were to graph the parabola, y equals a x squared plus bx plus c, the fact that we have equal roots means the vertex of the parabola lies exactly on the x-axis. Rather than crossing through the axis at two different points, the parabola simply touches the x-axis at only one single point. All right, we have reached the end of this lesson, so let's wrap everything up by reviewing our key takeaways. I hope this summary helps solidify your understanding of Case 2. Keep practicing, and I will see you in the next lesson.